Okay, this is question number 7.15 that there was a question about. So it asks to click on the electrophilic carbon that would be attacked by a nucleophile in a bimolecular reaction. Okay, so that means that we're talking about an SN2 mechanism here, and I just have some generic nucleophile that's going to attack one of these carbons. Now, the first rule is that the carbon has to be attached to a leaving group, and the carbon that it will attack has to be attached to a leaving group. Well, what are possible leaving groups? Possible leaving groups are halogens, because if the nucleophile comes in and adds to the carbon, it can kick off the halogen, and it will just become a halide ion, which is stable. So that would make this carbon a possibility. But then there are other types of nucleophiles that can be good leaving groups. And in the reading, a good leaving group is usually a poor base. And so what we know about halogens is that they're fairly poor bases, because if you think about HCl, what kind of acid is HCl? HCl is a strong acid. What does that mean? That means that when HCl gets added to water, it dissociates into its ions 100% or nearly 100%, and so Cl minus then is not much of a base. We know if we add salt to water, the chloride doesn't react with water to form hydroxide. And so basically the conjugate base of a strong acid like HCl is a non-base. So it doesn't act as a base. And so that's a great leaving group. There's another potential leaving group in this molecule, and it's this one. Because if you think about a nucleophile coming in and adding to this carbon, then the carbon-oxygen bond can break and the pair of electrons can go to that oxygen. That would make a molecule that looks like this. Now, that is what kind of base? Well, it's a very poor base. Why is it a very poor base? Well, we have to go back to basics on that and say, when you take an acid and you dissociate it into H plus and A minus, one of the ways to shift the equilibrium towards the formation of the H plus and A minus, and therefore increase the amount of dissociation, is to make this make this A minus molecule more stable. So the more stable that you make the conjugate base, the stronger the acid will be. And that's not a Le Chatelier issue, because Le Chatelier involves changing concentrations. In this case, I'm changing stability. So the more stable you make A minus, the more the equilibrium shifts, the more dissociation you get, and the stronger the acid. So if you take a look at this molecule right here, this, I would say, is a very stable anion. Can you guess why? Okay, have you guessed it yet? It's because that molecule has many, say it with me, resonance structures. And the more resonance structures you have, the more stable you are as a molecule. So just to show you one example, if we took this pair of electrons, moves it to the sulfur, we could move that pair of electrons out to the oxygen, and so that would be one of 3 total possible resonance structures for that ion. So this is a very good leaving group. Now, so which carbon is the nucleophile going to add to? Is it going to add to, let's say, carbon A that has this oxygen leaving group that has lots of resonance structures? Or is it going to attack carbon B to get rid of the halogen? Well, there's two things going for this. There are two things going for one of these two carbons. Number one, the bromide is a good leaving group, but this it's called a sulfonate group. This sulfonate group is even better because it has more resonance structures. So if this is a good leaving group, this is a very good leaving group. And so the easier you can displace the leaving group, the faster the reaction is going to be. So that's number one in favor of the CH2 attached to the sulfonate group. And this whole molecule would be called a sulfonic ester. Or actually it'd be called a sulfonate ester. The other thing that A has going for it is what kind of carbon is attached to the sulfonate group, a primary. What kind of a carbon is attached to the bromine, a secondary. And so, in this case, the nucleophile attacking the carbon and kicking off the leaving group is going to go faster when there's less steric hindrance around that carbon group. And so in this case, the primary is going to react faster than the secondary. So A is where this is where the reaction will take place. And the reason that it'll take place there is simply because the sulfonate group is a better leaving group because it has resonance structures and is more stable. And secondly, because it's a primary carbon, whereas the carbon attached to the bromine is a secondary carbon. And for SN2 reactions, primary alkyl halides, or in this case, primary carbons attached to leaving groups, react faster than secondary carbons attached to leaving groups. And so in this case, the CH2 attached to the O is going to be where the nucleophile attacks.